Okay, yeah, thank you so much for the intro. And yeah, this presentation was put together by my professor, Jessica Lundquist, myself, and our coworker, Nicoleta. We're all working at the University of Washington. And yeah, it was definitely a collaborative effort. So I'm excited to share with you guys a little bit about the snow energy balance. This is definitely an intro, and hopefully we'll have some fun. So we're going to start with using Poll Everywhere. And so if you guys have never used this before, essentially it's a platform that we can use to basically get some feedback during these webinars where we can't see or talk to each other, unfortunately. So if you guys can actually put your phone right up to this and scan this link, it should take you directly to a page that will have some questions that we'll use throughout the presentation. And if you don't have your phone on you and you're on your laptop, you can go ahead and go to the link, the polleverywhere.com/snow hydrology. And I think Nicoleta will put that in the chat. So you can go to that link and yeah, and get our polls. So the first thing we're looking at is basically where everybody is calling in from today. So yeah, it's like kind of lonely here. I am currently in Switzerland, actually, and I'm curious where everybody else is. Oh, we have somebody in Alaska and somebody else here in Europe. I'm not sure where that is exactly. Cool. Yay. Awesome. Yeah, so for some other folks, it may be very early in the morning or very late at night. Awesome. Yeah, I mean, our snow community spreads all across the US and the whole world. And it's amazing to see how we can all connect. So thanks for calling in and participating in this. So we'll use this and I'll be able to show you guys the results just like I did there throughout the presentation. And yeah, hopefully we'll be able to interact a little bit, even though we're online. So I'm going to start by introducing what we did last year for Snow School. So now it's online, unfortunately, but if you guys got a chance to ever work with Nick Rudder or listen to his talk last week, Nick last year taught us a little bit about the snow energy balance at Snow School 2020. And this is a photo of all of us laying on the ground, and Nick was like, all right, everybody look up at the sky and, you know, tell me what you see and how you think this impacts the energy balance. So I'm gonna try to do this with you guys right now. So imagine you're like outside your window looking up, you know, trying to see what components of the energy balance impact your everyday life looking outside. So maybe in this photo, if you're looking outside, you see something like this because it was really cloudy and snowy that day. But another day, it might be really clear or have some scattered clouds and look something more like this. And you might be like, Cassie, you're going out on a tangent. Why does this matter? Well, you know, this really does matter because all of these different situations are going to impact our snow energy balance. And so that's why, you know, Nick had us lay there and start thinking about these questions. So if we're thinking about sources of energy that go into the snowpack, there's quite a few things that we can start to highlight. First, we have something called sensible heat flux, which is the heat transferred between the air and the snow. We have latent heat flux, which is, can be frost or rime deposition and sublimation of snow from solid to a vapor or from a liquid to a vapor. You also have ground heat flux, the transfer between the soil and the snow. And these are all sources of energy that go into the snowpack. And something really big to highlight here is the net radiation flux. So net radiation flux is made up of two pieces, sunlight and infrared radiation. And really what we're going to focus on for this presentation is this net radiation flux. And research has shown, like highlighted here, paper by Nicoleta, where the energy from the net radiation is actually 5 to 10 times greater than all other forms of heat transfer combined. And so this is a plot here of like in the open, barren landscape, and in yellow is net radiation, and in red is, in yellow is shortwave, and in red is long wave. So you can really see those are so much greater than the latent sensible heat fluxes. So for this open situation. So that's what we're going to focus on for this presentation. But just note that, you know, there are other situations and different things happening potentially in the forest. And we're going to focus on here an open situation. So if you have your snow energy balance, if we're looking at this net radiation and you're in Nick Rudder's class looking up at the sky, what you're going to see is potentially solar radiation, which is in the shortwave spectrum. And so you have some shortwave being emitted by the sun coming in, and then you have shortwave coming out, and that's reflected from the surface. So these are the two components of shortwave, the solar radiation, and then you also have infrared. So this is long wave, and this is one component coming in is emitted by the atmosphere, which is then reflected. So you also have emitted, long wave emitted by the surface. So you kind of have, these are like your major components we'll be talking about of the snow energy balance, specifically in the open. And so all these, we have three components here where I write they're emitted by the sun or emitted by the atmosphere, emitted by the surface, and all these are emitted, they're emitted by bodies basically. And so something we talk about is black body emission. And so this refers to an object that emits thermal radiation. And this might be something you've heard about or maybe have never heard. And so basically, a perfect black body doesn't exist, but a perfect black body is sometimes what we use to estimate these things. So what you can do is you can look at Stefan Boltzmann's law, and you can look at the irradiance emitted by a black body. And how this is calculated with the temperature to the fourth and Stefan Boltzmann's constant. But of course, like I mentioned, perfect black bodies do not exist. So what we do is we use something called emissivity. So this is the efficiency of a body emitting relative to a black body. So it's that relative relationship between what you actually have and a black body. So what your equation now becomes for the what's being emitted by a real object is now actually your temperature to the fourth and still your Stefan Boltzmann's constant, but it's multiplied by this emissivity. So all matter, has an emissivity, and it's all within the range between 0 and 1. And it's always going to be less efficient than a black body because that perfect black body doesn't exist. But some things can be pretty close to a black body. So if you have water and ice and snow highlighted here, which are pretty close to 1, but then you have something like aluminum, which is a lot lower emissivity. And so you can see how using this estimation and talking about this in the form of snow, water, and ice can be very relevant. So if we're looking at emissivity and long wave radiation, we have this idea that all matter is actually emitting energy. And so if you have an increase in temperature, you're emitting more energy. And so if you have a higher emissivity, you're going to be emitting more energy. And so this is a cute little graphic where you have your person at 98.6 Fahrenheit, but then you have your snowpack at 32 Fahrenheit, which is 0 degrees Celsius. And that's the total amount of energy that's able to be emitted from that snowman and the snowpack is at 315 watts per meter squared. And this is because the snow's ability to shed energy through long wave radiation is limited by the phase change. So you cannot have a temperature of your snowpack greater than 0 degrees C. And then you can look at this person where you have a much warmer temperature and you're emitting more energy. So these are examples of different bodies that are emitting this energy. So if we actually look at bigger bodies, so something like the sun and the earth, and we look at the black body emission curves of these, we have two things being highlighted here. We have the solar shortwave radiation. So on the bottom x-axis is the wavelength, and on the y-axis is the radiated flux. And then you also have the terrestrial or long wave radiation. And you can see, like, going back to what we highlighted before about the net radiation, these are these two components of the major source of our energy balance that's going to be impacting the snow melting. And I think it's really important to highlight this here, the wavelengths here, because I think frequently we use solar and shortwave interchangeably and terrestrial or infrared and long wave interchangeably. And when you're learning about this, I think that can be confusing. So I wanted to highlight that here and, of course, say that our shortwave is between 0.2 and 4 micrometers, and that's your shortwave wavelength. And so this is actually why this is called this. And then you have your infrared radiation, which is going to be a much longer wavelength, between 4 and 5 micrometers. And if you break this wavelength up between what's actually visible light that we're seeing, that radiation that we're seeing, versus all these other options. So you have your shortwave existing in the visible light spectrum, but also in a part of the near IR spectrum. And then you have your thermal infrared, and your far infrared, which is where that long wave is existing. So we have our energy balance of our snowpack that I outlined before. If we start thinking about these components, let's do a poll everywhere, and let's think about what the shortwave emitted by the sun component, like what factors could impact this. So I think everybody should have this now. If you can scan this again and do what we did before, you should be able to type in and actually let me know what you think could impact the incoming shortwave radiation. I think you can, I'm not sure if you guys can see it, but I think you can upvote other people's answers and we can see which gets like the most amount of votes. Yeah, so I'm seeing air pollution, clouds, filtering from vegetation, trees. Yeah, these are all exactly what I was thinking. Cool, yeah, day of the year. Yeah. Cool. Yeah, I feel like you guys are here with me. Okay, so yeah, this is really great. Yeah, so if we're looking at these factors, so if we're looking at these different factors that could impact shortwave radiation, a lot of you just highlighted some really great ones. So what I was thinking, what I put on my slide, which people put way more in there, so it's great, which is season of the year, latitude, clouds, time of day. But, you know, of course, I saw a lot of other great things in that poll everywhere too, such as the air pollution or trees and all these other things. So yeah, so our shortwave emitted by the sun can depend on all these things. And so essentially, if you look at this figure where we have the Earth and the atmosphere, you can have these rays from the sun actually coming in at a higher latitude on Earth. And this is covering a much longer distance. They're traveling farther and they're they're covering a much larger area. And you can actually have the sun's rays hitting the Earth more near the equator where they're traveling a shorter distance and they're covering a smaller area. So this is just highlighting one of those that we mentioned, but of course there are a lot of other things. So we'll get to some of those later. So let's do the same thing since everybody is so great at this. And let's think about what factors could impact the reflective shortwave radiation. So this is a shortwave out component. So I think, let's see. Okay, should be active now. So just like before, put in there and upvote what you think could impact the reflective shortwave radiation. Yeah, albedo. I think that's gonna just get, yeah, great. Land type, I see also, sun angle. Dust. Surface roughness, angled incidence. And all the other albedos that are in there too. Cool, greenhouse gases. Types of snow. Yeah. Cool, okay, great, thanks guys. I completely agree with all those again. So what I was thinking was albedo. That's what I first wanted to talk about. And so everybody highlighted that and uploaded that one. So that's amazing. So we have this figure here where one part of it is looking at the snow surface that does not have any snow. So it's actually going to have about like 10% of that radiation reflected. So that outgoing is going to be about 10%, as opposed to if you have if you have something more, something of a lighter surface, such as snow, it's actually going to be reflecting a lot more like 85 to 90% reflected. So this is really what I wanted to highlight as far as what's really important for that shortwave out component. And now that we're talking about snow because of the snow lecture and not just all surfaces of the earth, if we're thinking about snow specifically, I think somebody mentioned 2 types of snow, which is snow metamorphism and age of the snow. And so that type of snow can actually impact how much is being reflected. So, not all snow is equal. And you can have impurities on the snow, which somebody else mentioned too. And so I think someone mentioned dust or dirt, and yeah, like dust on the snow. And so these are some photos that I wanted to include just to highlight like how different types of snow can impact this shortwave out component and your albedo. So you can have this really interesting stuff going on where you have lots of layers of dust on snow, and this is going to impact how much of that incoming shortwave is actually going to be reflective as outgoing. So I think this is, a really great visual example, but there's tons of other things I could go into that can really show how all these different properties of snow could impact this component. But I want to move on to the long wave. So this is the first component, which is the long wave in. So this is the long wave emitted by the atmosphere. So that's the atmosphere is that body. It's this atmosphere, so it could be clouds or just the atmosphere, which is actually emitting that long wave. And this depends on temperature, clouds. And you have your long wave emitted by the surface, which depends on the surface temperature of snow and ice. So if we're talking about long wave, we really need to start talking about clouds, because like I just mentioned, we have a long wave, which is emitted by the atmosphere, which is also involved with clouds. So if we have a clear sky, which Nick Rudder's teaching this lecture in the beautiful clear sky, but realistically the day looked like this for us. So we were looking up and the snow was falling on us and it was really cloudy. So how does this change our energy balance in this component of our energy balance? Well, clouds can impact shortwave radiation, which people had mentioned previously too, where you can have clouds that are actually reflecting the shortwave radiation, which is going right back out and never making it to the surface. And the largest thing, which I think we think of when we think of clouds, is long wave radiation. So you actually have the radiation being emitted from the surface and then being re-emitted by the lower atmosphere by those clouds and back down. And so often, this is something you hear about. This is the process you're hearing about when you hear about greenhouse gas emissions. Like this physical process of the long wave radiation coming in and out and being re-emitted by the atmosphere, and greenhouse gases in the atmosphere, such as water molecules, which is one of the huge ones, is going to impact how much long wave is going to be re-emitted back to the surface. So we have our cloudy day, and you're looking up, and it might look something like this. So this is the visible wavelengths of photo of essentially looking up and what you would see. What this could actually be is something like this, where you have a cloud temperature, and this is in degrees Celsius. And so you can have some pretty warm clouds, about around 5 degrees C, it looks like here. And so these images were taken looking upwards at Snoqualmie field site in Washington, which it's usually pretty cloudy there. So this is what you would see. And you have, this higher cloud temperature, and this is really equal to this higher emitted long wave radiation happening with the clouds. So this is kind of how we previously were looking at this clear sky. Now we have a cloudy sky. This is how this can be impacted and visually impacted. But then if we are talking about modeling and talking about how important these are for the snowpack, then how do we observe or estimate shortwave or long wave radiation? It's something I have just emphasized for the past, I don't know how long, about how important they are and how much they impact our snow energy balance and our snowpack, whether it's melting or not. And if we want to model this, how do we observe or estimate these things? Well, this is a beautiful slide by Mark Raleigh, which is titled Ideal Weather Station. And I really like this because I think this highlights what all of our hydrology dreams look like. And I think Nick and Alex talked last week a bit about weather stations and what we get from them. So I just want to highlight how this is related to what I'm talking about. So you have in yellow is your model foreseeing, and in blue is your model evaluation. So let's start here, which is a snow depth sensor and a snow pillow. And so this will be measuring your snow depth and SWE of your snowpack. Of course, if you're modeling for hydrology, you're going to be looking at your snow depth and SWE. So that can be used for model evaluation. Then you have your temperature sensor for your air, and you have your surface temperature, snow surface temperature. And then you have these other things such as your wind sensor, direction, relative humidity, precipitation gauge with a shield, of course, because this is our ideal weather station, and we're definitely going to have a shield on our precipitation gauge. And then you also have these. So you have your radiation sensors, and so you have your long wave and your short wave in, which these are going to be your model foreseeings, and then you have your long wave out and short wave out, which could be model evaluation points. So these things look something like this. So in the red is your long wave in, that's just your radiometer measuring this, and then the yellow is your short wave in. And these things are very expensive, and in our ideal weather station, we can put them everywhere. But in reality, they take a lot of maintenance, and you might end up looking at something like this realistically in the field. So you could have your radiometer covered in snow, and your solar panels even covered in snow in this one. And yeah, these things happen. And these radiometers, not only are they expensive, but they actually are, if you do have your ideal weather station, you can put them out, they have to be constantly maintained. And so they are at some ideal weather stations, of course, but in some situations, you end up with a situation like this, where you have your ideal station, and then you have what you typically have. So you might have precipitation and temperature and snow depth, which these are great for model evaluation, but something you really may be missing is something like wind and your radiation sensors and humidity. And this is pretty common. There's these SNOTEL sites, which people may have heard of, where a lot of them have your precipitation and in some cases wind, but temperature. And these are really, and your snow depth, of course, and SWE. So these things are really important for model evaluation. But if you really want to complete your modeling and have your full energy balance with these radiation components, you're going to need to fill this gap. So what we often use instead are empirical methods. We use for example, a shortwave can be instead use an empirical method to get shortwave. And then you have these other methods to actually get these values. So what they can look like, these other solutions can look like to get your meteorological data are there's something called HER, which people may have heard of. I've also heard it called HRRR, but I'm going to say HER, and which is it's an atmospheric model, which is going to give you your meteorological data. And there's other resources to also get something similar, something called WRF, which is very similar to get your meteorological data, and LDAS, which is I've also heard and seen used in the community, and something also called MedSim. So this is another example. This is a little bit different, where this is going to be actually using your daily minimum temperature, maximum temperature, and precipitation, which are things you can usually get from your meteorological stations. This is like our ideal versus our reality world. And you can use these things to actually calculate what we want, which is your shortwave radiation, your long wave radiation. So these types of solutions are out there and they're available. And I think they're pretty commonly used in modeling to kind of fill that gap that we previously talked about. Yeah, so maybe next time you will look up at the sky and you'll have a completely new perspective on what's happening. Yeah, thank you guys so much. I recognize that I ended very early, so I have a lot of other extra slides, and there's definitely time for questions, and I'd be happy to go into depth more about any of these components. But thank you so much for listening to the introduction of snow hydrology, the energy balance section. And this is my contact information if you want to find me. And Nicoleta and I are here for a bit to continue answering any other questions that you have.
Thank you so much, Cassie, for the nice presentation. I would invite everybody, if you have questions, to put them in chat. I was monitoring the chat to see if there's questions, and there were a bunch from Jessica that I want to address. Maybe one of the questions was how do you measure, I believe, solar radiation, shortwave radiation, when you have a solar eclipse? I think Cassie showed an instrument that's called I believe it's called Pyranometer. That is used to observe shortwave radiation. In a case of an eclipse, the solar disk is going to be obstructed, so probably the sensor is going to measure very little incoming shortwave radiation, potentially some diffusive component of the incoming shortwave radiation. That's a rare occasion. I'm not expecting that that's going to impact any snow analysis, but you can think of the snow on the dome of the instrument as a solar eclipse if you wanted to, because snow on the dome is a more frequent event that will affect your observations of incoming shortwave radiation. And so because of these mishaps and the maintenance that's required for these instruments, you may end up with gaps in observations. They could be filled with like empirical estimates or calculations of some sort. So a question that I see in chat is, what is the best method for classifying rain versus snowfall? A threshold for temperature or decreasing SWE? So this question is very important, especially now with the climate change studies that are going on. Temperatures are increasing, and being able to partition correctly between rain and snow is important. So at these locations, we can use various information to try to do that. But one of the things that's indicative of the precipitation phase is the temperature. If you think of a temperature threshold of 0 degrees C, typically you would say that below 0 degrees C, you would have snow, and above 0 degrees C, you'd have rain. However, that's not always the case, and you end up with a wintry mix or a mixed phase that's spanning a range of temperatures. Also, when thinking about this threshold is variable as a function of where you are in the world. And there's a really nice paper in Nature Communications that looked at that thing. For example, this threshold is warmer in the Colorado area versus the Olympics and the Cascades and California as well. There's another question from Justin. I work part-time with the snow survey, so just out of curiosity, you were able to add one sensor to SNOWTEL sites. If you were able to, why would that be? Yeah. In other words, what do you believe the biggest gap in data is coming from the SNOWTEL system?
Yeah, I think that's a great question. So in general, you can look at the SNOWTEL sites and see that you have snow depth, so the snow pillow that we're seeing here, and most common air temperature and precipitation. So I would say that's the most common, what you would see in some of the SNOWTELs. You can also see relative humidity and wind. And I also believe some of them do have radiation sensors, but I'm not sure, usually the SNOWTELs are in pretty hard to reach areas. And so that's what's really great about them. But if you have these radiation sensors in really hard to reach areas during the winter, then you have no one really maintaining them. So I guess if you were, part of the question is, what do you believe the biggest gap is? And I would say the least measured thing at all the SNOTEL sites would definitely be radiation. But as far as if I was able to add one sensor to the SNOTEL sites, I do not think I would add radiation, because if they can't be maintained, then in general, they're not going to be that useful throughout the winter. It's going to end up looking like the slide I showed where they're covered in snow. So instead, I would like to have probably make sure they all have relative humidity and a ventilated relative humidity and air temperature system, because I think relative humidity is a very essential part of all these calculations, and it would be useful to have that to then use that information for something like MetSim to then get long wave and short wave. But if somebody camped out at the SNOTELs all winter in a tent and cleaned off the sensors, I think radiation.
I got a request for the citation of the threshold. I'm looking for it. Please wait a second. In the meantime, Cassie, would you please talk about the availability of the slides? Some attendees are interested in the record.
Yeah, did somebody ask for them? Yeah, so these slides are a combination of something that Jessica, myself, and Nicoleta have put together. The video will be on YouTube, and if you need any additional information, you can email me. If you want, the slides themselves individually do not plan to be posted anywhere at the moment. So if that's something that's highly requested, we can look into that. But at the moment, the video will be immediately available, and then you can contact me here at my email if you need further information beyond
that. There's another question. Can you talk about the role of temporal resolution in the snow modeling? I guess I could address that. So we talk a lot about temporal resolution, but also spatial resolution as well. And this depends on the application. It depends on what you want to study. Typically, hydrologic models that have a snow component have temporal resolutions that range from daily to 3 hourly or hourly. If you are applying your snow model for an avalanche type of application and running it at a point location using a lot of snow layers, and it's computationally intensive, you need to represent these processes as best you can. So I would maybe recommend an hourly or sub-hourly time scale. If you're running a hydrologic model with a snow component over a large area, then a model with a simplified layering scheme and would work and maybe also applied at a daily time scale. So I think that all these applications are, all these models are important in the sense of how you're using the data. But now I'm thinking that you're referring to the sub-daily temporal resolution, because if you want to represent the solar incoming solar radiation, you would like to do a sub-daily time step. Is another question. I have never seen a precipitation gauge with a shield on top of a tower. Is this a normal practice?
Yeah, I guess in short, I've primarily seen your tower with your booms hanging off with your sensors, and then your precipitation gauge lower to the ground, kind of separate with your shield around it. But I'm not sure, Nicoleta, you might have.
The shield around the precipitation gauge is used to address the undercatch problem, because, for example, the wind is transporting the snowflakes above the precipitation gauge, and if you can slow it down, it can enter a lot more into the precipitation gauge. So you don't have this problem of precipitation undercatch as much as you would have it without the shield. Now there's different types of shield configurations, and maybe not all the precipitation gauges have shields, but I believe the SNOTEL ones have.
Yeah, I think, yeah, I'm not sure what the question was referring to, but I did see, I think Andrew might be referring to whether or not on top of the tower is the place that you would normally see this. I'm not sure if that's what he was referring to, but as far as the shield goes, Nicoleta answered that really well.
It's a question from Will. I had to step out for a minute, so I might have missed this, but do you know if all SNOTEL sites use snow pillows, or do some of them only use standard precipitation gauges without snow pillows? I believe that all of the SNOTEL sites have snow pillows because that's where they're supposed to be measuring snow.
Yeah, the SNOTEL sites, to my knowledge, all have snow pillows, and that's primarily why they're set up. They're set up the way they are with snow pillows, and most of them also have temperature precipitation gauges. But I don't know. I don't believe that there's any that are just precipitation gauges without snow pillows, from my experience. But
I think I might have missed some questions.
Yeah.
I have a question. How would so this is from Niran. How would you how does energy balance behave when the site is a glacier instead of a ground with snow? So it will be the same, right? This is the energy balance at the air snow interface. It would be at the glacier air interface. However, there'll be different ways to represent glacier processes. We're just talking here about snow. But the energy balance components are going to be the same. Just the receiving surface is going to be different with different snow albedo.
Yeah, I see your question. Would you please let me know if there's you have a suggestion regarding how to check precipitation suite temperature data for quality at any SNOTEL site? Yeah, I think that's a great question about quality of our meteorological data. And some things that I've done in the past is compare them to first what you have nearby. If there's something else nearby, the SNOTEL sites are typically in remote locations for a reason, because it's where gaps are in our snow information. So what you could also do is get information from a different resource, which such as a atmospheric model like HER or WARP, and compare those for that point location and see how your values look. Yeah, and I guess, Nicoleta, do you have any other suggestions for how you would actually check your quality for your SNOTEL sites?
I just have to mention the paper by Euler et al. 2015, where they found a bias in the SNOTEL air temperature observations, and a way to correct it. So I would check that paper, and if you're thinking you're using a sensor that has a bias, I would take care of that, especially because we are talking about that partitioning between rain and snow, and errors in air temperature could lead and errors in this partitioning, and you'd have more snow or more rain. So that's what I would do for air temperature. I was just trying to see if I missed any questions. Here's a question from Charlie. How often are models evaluated for closure of the energy balance? For example, snowpack temperature, liquid water content. I'd say from my experience, maybe I'm wrong, I don't know, I think rarely. I think that, for example, the sublimation is a term that's often misrepresented or has high uncertainty in the models, and it's hard to quantify that. Again, for snowpack temperature and snow surface temperature is a measure of the energy balance and a measure of how much energy is contained in the snowpack, but it is very hard to close the energy balance. So people have applied these models at these idealized or ideal maybe sites where you have plenty of observations. However, if you're applying a model over a larger area, you'd have to extrapolate these observations to represent other areas. And the problem of energy balance closure is becoming even more complicated when you don't have high quality data, especially with approximations of albedo. That's something that albedo is rarely observed, and you have to distribute that to be able to run a model spatially. Similarly, with the incoming long wave radiation, that's rarely observed because it's expensive, and you would have to somehow estimate it. And these estimations are based on empirical models that use air temperature and relative humidity, and sometimes they are developed for specific sites, and site transferability is a big question. I think that even if you can maybe close the energy balance and the mass balance at a point, distributing it would be hard. So I think we're getting there, and I think the remote sensing products are going to help with closing the energy and mass balance in our models. But I think there's still work to do. Is a question about, is there any reliable method for remote sensing of snow depths? First, at some stations, there are sonic anemometer. How they're called? Anyway, there are sensors that can measure snow depth. However, sonic sensors, yeah, sonic sensors. However, more recent technology employs LiDAR, and snow depth can be observed spatially with terrestrial LiDAR or airborne LiDAR over larger areas. There is uncertainty in those snow depth observations as well, that ranges between 1 centimeter and maybe to 8 or 10, or if you have shrubs or short vegetation, it could be higher. However, that's an excellent way to understand spatial variability of snow depth, but it's expensive and it's happening only on select areas. Thank you. It would be great if there's any slide with a complete list of references. Okay.
I think that's the references. I think that's referring to the conversation about actually checking the quality of the SNOTEL data. I think that's what that's referring to. So I think it's directly referring to the citations for the paper that you just mentioned to check out.
I'll make the citations available.
Yeah. Cool. Yeah, I think that was it. Great. All right. Awesome. Yeah, thank you, Nicoleta. And yeah, thank you everybody for your awesome questions. Did we miss anything, Nicoleta? Or
I'm not sure. It went really fast, so I was trying to talk and look at the questions at the same time. So I apologize if I was doing two things at the same time. So I put in a chat the link to the rain versus snow threshold, and I will find the SNOTEL paper immediately.
Okay, yeah, maybe we can link them. We could link them with the YouTube video, maybe that comes out, or yeah, just email me or Nicoleta if you need those directly, if they don't come out when you need them. But
I think that there was a question regarding the dust on snow that I missed. Was the origin of that dust? Cassie, I think you can respond to this one.
Yeah, well, I am not sure if I see it. Is it regarding the origin of the dust in those photos? Is that what Oh, yeah. Yeah, without going back to the photo. So those photos weren't taken by me. I am unaware of exactly the origin. I put the citation for where those came, where they did come from, though I could go back to it. Yeah, I didn't take any photos recently, but I am currently in Switzerland visiting SLF, and we have some dust on snow events happening right now too. So Yeah, this one is in the San Juan Mountains in Colorado, May 2009. This was taken by Mackenzie Skiles. So Mackenzie, if you're listening, thank you for your beautiful photo about dust on snow. Yeah, and so this other one, I'm not sure of the exact location. I'm sorry, yeah, their photo I did not take, but this is actually in the appendix of the papers that are referenced here. So if you go look at that, I could find out. But yeah, at least for the dust on snow that's happening in the top photo, that's in Colorado.
There's a comment from Timothy. I would think satellite data could also be used to estimate spatial distribution of shortwave and longwave radiation. Well, it depends. Yeah, ideally, yes, but I think it depends on the scale. Like these models are applied at high spatial resolution. I believe there's some shortwave data that we actually used and from the Cirrus product that I think it worked. And the long wave as well. So we checked the long wave from the Cirrus product, I think in the Tuolumne area, and that was good enough for representing observations. So I think that in the future, yes, the satellite products may have may play a more important role in running these models.
Cool, yeah, sorry I missed that. Thank you for catching that. Great.
I'm not sure if I missed any questions. I hope not.
Yeah, I guess if we did, it would be good just to repost them in the chat so they're at the bottom if you had anything else you wanted to add before we wrap up today. I'll go back to my original slide. Cool. All right, I think we're all set then. Doesn't look like anything is coming in. Awesome. All right. Thank you so much, everybody, for listening. Thank you for your awesome questions. And thank you, Nicoleta, for your help, and Jessica as well. I'm going to stop sharing my screen.
Thank you for attending.
Yes,
yeah, thank you.
Everyone have a good weekend. Thank you.